very good morning, students. Today in this lesson we'll be learning about density in the ocean waters. The density of any material is defined as the mass per unit volume. Thus, in the CGS system, density is measured in grams per cubic centimeter. The specific gravity is the ratio of density to that of the distilled water at a given temperature and under the atmospheric pressure. In the CGS system, the density of distilled water is at 4 degrees Celsius is equal to 1 unit atmospheric pressure at about 4 degrees Celsius. The density of the pure water at 4 degrees Celsius is the greatest. In oceanography, specific gravities are now always referred to the distilled water at 4 degrees Celsius and are numerically identical with the densities. The density of the sea water depends upon the temperature, salinity, pressure. It is noteworthy that the density of the distilled water is greatest at 4 degrees Celsius, whereas sea water is most dense at a lower temperature. Since the sea water contains dissolved salts, its density is greater than that of the distilled water at the same temperature and same pressure. After going through this lesson, you will be able to understand the density of the sea water, the factors affecting it and its distribution. In the case of the liquids, it is the density that determines whether an object sinks or floats on it. However, the sinking rate depends on its relative density and also on the resistance it experiences while moving through the water. In the oceanography, the density is expressed in the terms of sigma, which refers to the density at the atmospheric pressure and the temperature at which it was collected. The term sigma is used for the value correction to the atmospheric pressure, while sigma refers to the density of the water that would have at 0 degrees Celsius it would have had in this form. The density is only a function of salinity. For most purposes, sigma is the most useful as both temperature and salinity are the controlling factors of the density. At the surface of the ocean, the density is always fairly close to 1 and varies according to the salinity and the temperature and the pressure. However, the density of the sea water ranges from 1.02 to 1.03 gram per centimeter cube. The average density of the surface water in the oceans is about 1.02 gram per cc. Any increase in the salinity or the pressure results in an increase in the density. On the contrary, a decrease in the temperature of the sea water causes an increase in its density. Despite the maximum salinity in the sea water in the subtropical regions, there is a regular increase of density from the equatorial regions towards the poles in all the oceans. Thus, it is obvious that the temperature has a decisive control on the density. It may be stated that whereas the density of the pure water is dependent on the temperature and the pressure only, that of the sea water is influenced by the combined effect of temperature, pressure and salinity. Salinity is therefore an additional variable that adds a new dimension to the density control of the sea water. Besides the aforementioned major factors, the density of the sea water registers an increase as a result of cooling, evaporation and the formation of the ice. On the other hand, the density decreases with the addition of the fresh water from the precipitation, melt water or the runoff from the land areas. Let's bear in mind that the density of the ocean water plays a very important role in determining the circulation pattern in the oceans because of the fact that the differences in it cause lateral displacement of the water. Since warm water is less dense and lighter than the cold water, it has a tendency to float on the colder and the denser water. Similarly, cold or highly saline water at the sea surface tends to sink and be replaced by the warmer and the less saline water. This tendency results in the different patterns of the surface water movement that undergo seasonal changes. The difference in the density of the surface and the subsurface layers produces vertical convection in the oceanic water. This process is called the thermohaline convection. Another characteristic feature of the density of the ocean water is that even though a decrease in its temperature increases the density, after attaining the freezing point, any further increase in the density stops in the deeper layers. Thus, it is clear that at constant temperature and pressure, any change in the salinity results in density variation. Factors controlling the density of the ocean water. First factor, the temperature. Temperature is the most important of all the factors that has an important influence on the density of the oceanic water. In the open ocean, in general, it is the temperatures that determine the distribution pattern of density. That is why the temperature and density distribution in the open sea shows similar characteristics. There is a gradual and regular increase in the density of the seawater from the equator towards the poles. In spite of high surface salinities in the subtropical regions, there is no increase in a thermally produced low density of the seawater there. It is undoubtedly true that if there are large differences in the densities of the adjacent water masses, they cannot remain in equilibrium. The horizontal variations in the surface's salinities result in large scale water movements in the oceans. Next factor, salinity. Salinity is another very important factor that influences the ocean water density. At a certain temperature, the density increases with increasing salinity. This is due to the fact that the components of the salinity have a greater density than the distilled water. It is well known fact that at 4 degrees Celsius, the density of the pure water is 1 gram per cc, but when some salt is dissolved in it, the salt water thus created will have higher density. This is so because the salt water is heavier than the pure water. At the same temperature, therefore, the sea water will be denser than the pure water, which always floats upon it. Now, it is clear that any further increase in the amount of salinity of the sea water results in the corresponding increase in its density, even though the temperature does affect the density. It is to be borne in mind that 4 degree temperature with 35 parts per thousand salinity, the density of the sea water is 1.02 gram per cc. However, if the salinity is reduced to 20 parts per thousand, then its relative density will also be reduced to 1.016 gram per cc. For example, in the Caspian Sea, the Red Sea and the Mediterranean Sea, the salinity is high due to the higher rate of evaporation. Pressure. Pressure is another variable which controls the density of the seawater because the pressure and compressibility of the seawater are very closely related. Any increase in the air pressure will bring the different layers of the water closer together due to mutual pressure. Naturally, it results in an increase in the density since volume of the water decreases. It is worthwhile to remember that there exists a very close relationship between the temperature and the pressure and the salinity of the seawater. The higher the temperature, the lower the air pressure. Similarly, the degree of salinity directly affects the density. However, the density decreases with decreasing air pressure. On the contrary, in case of any decrease in the air temperature and the increase in the air pressure, the density is bound to be high. If the density of the surface water is higher than that of the adjacent subsurface layer, vertical convection occurs leading to formation of a layer of homogeneous water. In areas where intensive cooling occurs at the surface, the vertical convection currents move to greater depths until the density from the surface to the bottom attains homogeneity. Convergence and divergence. The processes of convergence and divergence exert an important influence on the density distribution in the oceans. Vertical movement of the water masses are due to either the differences in the density at various depths as pointed out earlier, or due to the meeting of two types of currents converging upon one another, thus causing sinking, which must be counterbalanced elsewhere by ascending currents. In areas where convergence occurs, waters of relatively higher density moves downwards. On the other hand, in the areas of divergences, the ascending motion of the bottom water brings water of higher density and lower temperature towards the surface. This process is called the upwelling. This process is generally the result of the offshore winds. The divergences are most clearly observed off the west coast of the continents, where the trade winds drive the warm surface water westwards. Similarly, in the westerlies, this process occurs along the east coast of the continents. Other minor factors, in addition to the above stated major factors, there are some minor factors which also affect the density of the seawater. For example, the rainwater, the surface runoff brought by the rivers flowing into the oceans, and meltwater from the ice and snow deposited on the ground are such minor factors which contribute lowering down the density. On the contrary, evaporation, cooling of the surface water and the processes of ice formation tend to increase the density of the ocean water. Since temperature has the greatest effect on density, density profiles are usually mirror images of the temperature profiles. Density is lowest at the surface where the water is the warmest. As depth increases, there is a region of rapidly increasing density with increasing depth, which is called as the pycnoline. The pycnoline coincides with the thermocline as it is sudden decrease in the temperature that leads to the increase in the density. Below the pycnoline, density may be fairly constant or it may continue to increase slightly towards the bottom. The profile above, which was just shown, the figure, that represents a stable state or high degree of stratification where the warm, low density layers sits atop the colder and the denser layer. If denser water happened to form at the surface, the water masses would be unstable and the denser water would sink to the bottom to be replaced by less dense water at the surface. This vertical movement of the water masses based on the density as determined by the temperature and salinity is referred to as the thermohaline circulation. By creating a stratified water column, the thermocline and the pycnoline create a barrier that prevents mixing between the warmer, less dense surface water and the colder and the denser bottom water. In this way, nutrient-rich deep water may be prevented from coming to the surface to support the primary production. As with temperature, there are also latitudinal differences in the density. In the tropics, the surface water is warm and low density and there is a pronounced thermocline separating it from the colder, denser, deeper water. As stated above, this stratification prevents nutrient-rich water from reaching the surface and as a result, the tropical regions often have low productivity. In the higher latitudes, the water is uniformly cold at all the depths. So, there is little density stratification. The lack of a pycnoline or a thermocline allows cold, nutrient-rich, deep water to more easily mix with the surface water, leading to higher primary production in the polar regions. Horizontal distribution. In the tropical regions, the temperatures are uniformly high throughout the year so that the density of the surface water is very low. The result is that despite increasing convergence, water from the surface cannot sink to greater depth but spreads out at a shorter distance below the sea surface. Thus, there forms a sharp boundary between this less dense and lighter top layer and the denser water at some great depth. In that tropical open oceans, the surface water is characterized by low density because of its mixture with the fresh water. However, in some isolated adjacent seas like the Mediterranean Sea and the Red Sea, the evaporation is very intense. The result is that even a moderate cooling in the winter leads to the formation of bottom water with relatively higher temperature and salinity. So is the case in the interior part of the Gulf of California. If such seas communicate freely with open oceans, deep water returns to the open oceans as a subsurface flow. Since the Mediterranean Sea is the typical area having this type of circulation, it has been rightly called the Mediterranean circulation. In the case of the Red Sea, still depth at the Straits of Bab el-Mandab is only 125 meters. Across this shallow sill, the basic circulation is subjected to high rate of evaporation. Thus, the loss of the surface water in the Red Sea must be compensated by the Indian Ocean water from the Gulf of Aden that enters as a subsurface flow. Winter is the season when this condition is present in most developed form. During winter, south or southeasterly winds move across the southern Red Sea. As the surface water moves north, its density is increased as excessive evaporation increases salinity. This dense water sinks and flows out in the Gulf of Aden as a subsurface flow. This outflowing saline water ultimately spreads out into the Indian Ocean. In the middle latitudes in the open oceans, the density of the water is low because of the excess of precipitation and high temperature. The result is that the convection currents are confined to relatively thin surface layer and do not lead to the formation of the bottom water. Of course, the formation of the deep water occurs mainly in the high latitudes where the excess of temperature in some of the regions does not permit the formation of convection currents that are strong enough to penetrate to greater depths. The Gulf Stream carries water of high salinity into high latitudes. In the Irmingner and the Labrador Seas, this more saline water is partly mixed with the cold water of the low salinity flowing out from the Polar Sea. In winter, when this mixed water with high salinity is cooled, convection currents are capable of entering from the surface to the bottom, forming deep and bottom water that has a high salinity and a temperature much above the freezing point of water. In the Arctic, whenever freezing occurs, the salinity of the surface water is very low because of the fact that a huge quantity of fresh water is carried into the sea by the rivers originating in Siberia. Convergence also affects the density of the surface water. In the tropical regions, the convergences do not increase the density. Even though the surface water sinks, it is not able to reach the deeper layers because of the presence of the pycnal line. Thus, the development of the denser water occurs at some distance below the layer of the rapidly changing density of the pycnal line. It should be borne in mind that the most powerful convergence is the Antarctic convergence, which takes place all around the Antarctic continent. The sinking water at this convergence has a high density and spreads over the bottom deep water and can be traced in all the southern oceans at depths between 1200 and 800 meters. The density of seawater plays a vital role in causing the ocean currents and circulating heat because of the fact that dense water sinks below less dense water. Salinity, temperature, depth all affect the density of the seawater. Density is a measure of how tightly a certain amount of matter is packed into a given volume. The more the stuff is packed in, the higher the density. Density can be calculated by dividing an object's mass by its volume. It is commonly measured in grams per millimeter or grams per cubic centimeter. High salinity makes water denser. This is because there is more salt packed into the water. High temperature makes water less dense. As water gets warmer, its molecules spread out, so it becomes less dense. As it gets colder, it becomes denser. Most chemicals get denser when they turn from a liquid to a solid, but water is different. When liquid water freezes into the solid ice, it becomes less dense. When ice forms, water molecules arrange themselves into a rigid but open pattern. This structure is less dense than the liquid water, so ice floats. Deep water is denser than the shallow water. The water molecules are packed together more tightly because of the weight of the water above pushing down. Thus, in today's lesson, we have learned about density, its different factors and its distribution.